In this session, we'll talk about computational issues, convergence issues, and how you can do automated runs in Anaqsim. We'll talk about the speed of computation and what governs that, what amount of memory is needed for different scale models, how you can save a solution once you've solved it and then come back and later load it with that enables you to skip the solve step, which can be time consuming. Some solve and check settings, what they are and how to adjust them, and some convergence guidance for how to get around convergence issues, and a bit about making automated runs, which can be handy for calibration and other Anaqsim tasks. Let's talk about a few things that affect the computational speed of Anaqsim. The biggest computational burden in Anaqsim is solving the system of equations. And in Anaqsim, that is an n by n system of equations, n unknowns, n equations. And it is somewhere between fully populated and medium sparse, depending on how many subdomains you have and so on. But solving an n by n matrix using the kind of solvers that work on a nearly fully populated matrix requires computation and time that is proportional to somewhere between n squared and n cubed. So the amount of computation goes up pretty rapidly as the number of equations goes up. And whenever you're solving, you typically have multiple iterations to solve the system if you have any nonlinear equations in there, which you would if you have an unconfined or a fresh salt interface domain in it. And each time that you solve the system, say once for a steady state, it requires iteration because some of those equations are nonlinear. When you're doing a transient simulation with multiple time steps and periods, each time step is like solving a steady state system. It has to iterate at each time step. And so the computational burden can get fairly large for transient simulations with a lot of time steps. If you keep your number of equations under 10,000, then it will be able to solve each iteration in minutes or less. And if you venture further up the scale and have 20,000 or more equations, each solve could take as much as 10 minutes or more. And you can't give hard and fast guidelines on these because the machines people are using these programs on vary quite a lot with how much memory they have, how fast their processors are, how many processors or how many cores per processor, and so on. So it also depends on how many multitasking things you're doing on this computer at the same time. When you have fewer tasks, it'll run faster. So I can only give ballpark guidance here, but in general, fewer equations is very helpful. So you want to be very careful about kind of optimizing and minimizing the number of equations needed to solve the problem at hand. Also, when you have a system that is more linear, and that's generally more confined domains, which tend to generate all linear equations, more confined domains, fewer of the nonlinear, unconfined, and fresh salt interface domains, you will need fewer iterations. So the bottom line is that the more complex your model, the more equations there will be, the more accurate it will be, but also the slower it will be. So I like to create models with as little complexity as possible, but I do want enough complexity so that I'm not overlooking some key aspect of the system. Like often a two-dimensional model, a single layer model, isn't good enough. You really need to go to multi-layers, or maybe a steady state model doesn't really address the issue at hand. You need a transient model, and so on. When you're building your model, I would always recommend to start out very simple and move by baby steps up the complexity ladder. And that way, if you're running into trouble with convergence or something, you probably know what's caused the non-convergence because it's the thing you just added, the little new additional thing. So that's good guidance. While you're developing and refining a model, you can get away with less accurate modeling. Use coarser basis point spacing, fewer layers, fewer parameters per line, fewer vertices, and so on, fewer time steps. That'll save you a lot of time in the modeling process when you're doing run after run, refining and adjusting. And then when you get kind of the product that you want, you're very close to what you're answering the questions you need to answer, then you can make prettier and more accurate outputs for a report by basically ramping up these kind of factors, your basis point spacing, the parameters per line, vertices, and layers, and so on. So that's a good approach. So you're not spending a lot of time twiddling your thumbs waiting for the model to solve. You do your bulk of your work with a stripped down, simpler version. A while back, I and folks at McLean Environmental did a bunch of experiments to see how big a system of equation you could solve with an Anaqsim as a function of how much memory your computer had. And we came up with this graph, and that may or may not be somewhat different today. I don't know. I haven't run these kind of experiments in several years, but this gives you general guidance that if you've got, say, 8 gigabytes of memory, you can get up to somewhere around 17,000 equations. If you have 32 gigabytes of memory, you can get up to 38,000 or so equations. There is an upper limit of 46,000 equations roughly, and that is imposed by the operating system and Microsoft's .NET environment, 64-bit. And there's no getting around that one. That's a hard stop. One feature that's very helpful when you're running more complex models is the ability to save and then later reload the solution. So once you've solved the model, you can save the solution, which is a binary file with a .solu extension, and then come back a week later and open up the .anaq model input file and also load this solution file, and then you are at the point where you can examine outputs, make graphs and plots, and so on. And you don't have to go through the solve step. You can basically cut that out by loading the solution file. And another nice feature of this is that you can load the solution file in the light or free version of Anaqsim if that solution file may have been created with the full-blown deep designer version of Anaqsim. That doesn't prevent someone with the free or light version from loading that solution and examining it. They wouldn't be able to solve that model, but they can load the existing solution and make plots and examine outputs. This can be handy, for example, if you want a regulator to have access to the model you created. You could send them the model input file as well as the .solu file. They could open it up with the less expensive version of Anaqsim and examine the model. Under solve settings, there are some inputs that bear explaining. This term, the under relaxation, is a factor that you input that determines how far the element strengths will move from one iteration to the next. If you put in 1.0 there, then the strengths at the newest iteration will just be what they are at the end of that iteration. If you put in something less than 1.0, like 0.9 here, then the strengths, the element strengths, will move 90% of the way from the previous iteration strength to the latest solve strength. And this can be helpful to kind of dampen some oscillations if they tend to develop, and this tends to be helpful in some of the more complex models that people create. For simple models, just putting 1.0 in for this will probably solve in the fewest iterations. But if you're running into convergence issues, you might want to reduce this down as low as 0.7 or 0.6, but somewhere in that range, 0.6 or 7 up to 0.9. And that could allow it to converge where it wouldn't with this set at 1.0. If you have a model that's all confined domains and you set this to 1.0, it should solve in one iteration because all your boundary condition equations are linear and it won't require iteration. When you have more complex models with nonlinear domains and boundary conditions, and possibly some dry up issues where you're getting nearly zero saturated thickness, that can be a greater challenge to convergence, and that may be a case for reducing this under relaxation parameter. When an Anaqsim solves a system, it continues iterating until these check setting conditions are met at every boundary condition. And basically, there are different values for different kinds of checks. The head check tolerance is length units, and that is if you specify a head, say at a line boundary, at each control point, how close does it have to get to the specified head? And that's what this parameter is. You have different units where we're checking the discharge, capital Q. That would have discharge units, length cubed per time. You have normal component of discharge, check tolerance here. That is discharge per length of line boundary, which has units length squared per time. And then you have an extraction check, which is the basis point equation at each basis point in a SVAS, and that is discharge per area, which has length per time units. So make sure you put in reasonable values for each of these parameters. If you put it in too small, then it's going to take more iterations to meet those criteria. If you put it in too large, it'll take fewer iterations to meet those criteria. But if you go way too large, then you're not getting the boundary conditions met as accurately as you'd like. So somewhere in the middle is the sweet spot, and it just takes a little practice with that to see the default units that are put in there make pretty good sense for feet, meter, and day units. Convergence issues are the bane of groundwater modelers' existence, and they crop up no matter what kind of software you're using. But as I said, with Anaqsim in simpler models, convergence is generally good, and in 6 or fewer iterations, very commonly 4 or 5 iterations. If it's all linear confined domains, it should be 1 iteration. When you get into more complex models, that may start to go up above 6 a little bit. Rarely, if it goes as many as 20 iterations, would even more iterations be a help. If it's not going to converge in 20 iterations, it's probably not going to converge. In a couple of slides ago with those solve settings, I typically set my maximum iterations to 20, sometimes 10. And as we said, nonlinear boundary condition equations require more iterations. And basically, the more difficult the task is that you're asking the model to do, like if they're really large conductivity contrasts or really tight twists and turns in the flow field required, that may require more iterations to solve. When you run into non-convergence, here are some strategies that can help you figure out what to do. First, I would check the boundary conditions at all of your boundary condition equations, and that's something you access under the analysis menu. And, that would be the second bullet item here. Before you do that, though, I would make sure that your model construction is what you hope it to be. And I would check that your boundary conditions and your domain external boundaries are right. I'd rove around the model in each of the layers of the model to make sure that the domain that I'm in as I rove around with the cursor is where I think I am. And if it's not, you probably have external boundary errors going on. You can also make head contour plots of the solution after non-convergence. Even though it doesn't converge, it will go with the latest solution that's in memory from the last iteration. And that may help point out where in the model things aren't converging. You may get, some kind of blown up heads around certain boundaries that are not behaving or something like that. And also, when you check the boundary conditions, the second item here, it will give you information about which boundary conditions are not converging. So that'll help you home in on where the problems are. When you know where the trouble areas are, you can go to those and improve the accuracy. You can add more vertices or more parameters per line to line boundaries. And you can use smaller and denser basis point spacings for your area sinks, your SVAS. And as I said before, just good practice is to slowly increase your model complexity by small steps, solving between each step, so that you know that it's probably the most recent step or bit of complexity that you've added that is the culprit in the convergence problem. And once you found out where the problems are, I would reduce the complexity of your model and think about how to reduce the number of equations in your model so that it's just simpler and easier to manage. Anaqsim can be run from a command line, basically an automated run, as opposed to using the user interface and pointing and clicking on menu items and so on to do the sequence of tasks you want to do. You can basically set up a text file that tells Anaqsim what tasks to do, and it does it in the background. So that's a very handy feature, and it's written up in the user guide under computational details. And basically one text command line opens up the model, solves it, and writes various outputs to a text file or to graphs, and there's really quite a lot of capability there. Here's a listing of the different things that can be output. You can output the well discharges and or their heads to text or to a graph. You can output line boundary discharges and or heads to text or graph. That would be, discharges of river reaches, individual or grouped ones, for example, or discharges within a drain, for example. Lots of different possibilities there. If you're running calibrations, you can output the calibration statistics to either text or a graph. If you want to make a plot of conditions along a line, and that might be a profile with heads, domain boundaries, fresh salt interface, path lines, lots of different possibilities there as well. You can generate text or a graph for that. You can make head or drawdown hydrographs, output to text or graph. You can list the captured path lines in text. You can write the vertical leakages over user-specified polygons, output to text or graph. You can do the same with external line boundaries, all the external line boundaries in the model. You can output head data, the data that is the basis for contour plots, thousands of points where the solution is evaluated. You can output that in text format, in binary format, or in a Surfer software format that you can just load right into Surfer and make contour plots outside Anaqsim that way. You can run the check of boundary conditions and have that output to a text file. You can tell Anaqsim to save the solution into that binary solution file. All of these things are possible. Some other resources you might turn to for learning more about automated runs, and in particular using them in conjunction with parameter estimation software like PEST, and that is very useful for speeding up your model calibration process. At my website, I've got this link to a page here with a couple of examples. And the Flex AEM tutorial series has one particular session on using PEST with Anaqsim. So these two links here will steer you into some more detail in this regard.